Our next speaker will be Rajagopal Nagarajan, from QUÄNTANGLE, which is a new startup of yours. Is that right?
Yeah. Relatively new startup in the area of quantum software and quantum security. And I think people here will appreciate the E and the A in the logo, right? It took me a long time to come up with that. Okay, so I'll talk about modeling and verification of quantum systems. So formal verification for reasoning about correctness and security of classical system has been there for a long time. And as we know, used by companies like Microsoft, Amazon here, Intel, NASA, etc. So many years ago, nearly 23, 24 years ago, I asked myself the question, can we do something similar for quantum computing and quantum cryptography? So general purpose, large scale quantum computers are some years away. RSA is not really under threat right now, maybe 5 years, 10 years down the line. And big push recently by companies such as IBM and Google, etc., for quantum supremacy, right? So to give you a little bit of an idea of what's happening here, so there are quantum computers developed by IBM, Google, and various startups like Quantinuum, Rigetti, various kind of companies. And these are at the moment called NISQ computers. So NISQ stands for Noisy Intermediate Scale Quantum Computers, okay? So this is a picture of an IBM superconducting quantum computer. That's the chip. Okay, and Google has its own superconducting quantum computer. The latest chip is called Willow, and Rigetti is a startup. And I'm mentioning only really superconducting quantum computers, but there are, of course, other technologies such as ion trap or neutral atoms. Various companies are working on that. And these things are really have only very small number of quantum bits, like from maybe 50 to IBM has about 1,000. And these quantum bits are really noisy, prone to errors, okay? And there are already emerging applications to various fields, such as drug discovery. You can simulate molecules a bit faster. You can do quantum machine learning better, and you can do some optimization, solve some optimization problems. Okay, so these are just still not full-fledged applications yet. Okay, because the computers are not fast enough. And in general, you have a full stack, right? With a quantum computer, going from an application layer through to some compilation assembly kind of thing, down to a QPU, a quantum processing unit. And there are some control systems for these units, right? So this is what is known as a full stack, software down to hardware. And of course, each component, and as well as the whole system, needs to work correctly, right? On the other hand, you have the field of quantum communication and cryptography, okay? This is a mature field. It's been around for maybe 20 to 30 years. And this is just sending secret keys over a quantum channel, right? They're encoded in photons typically over fiber optics. And the idea is the eavesdropper, if there is an eavesdropper, he or she will be detected. There's not much computation going on, so you don't really need a quantum computer for that. And QKD, this quantum key distribution, is unconditionally secure. So it's been proven to be unconditionally secure. But implementations, we don't know, right? People are implementing, like this is an implementation by Toshiba. So in theory, it's unconditionally secure, but in practice, is it secure? So that's why we need techniques like formal verification. So many years ago, I worked on a project. This is a quantum communication network, key distribution network around Vienna, this around 2006. That was built already then, right? And then BT and Toshiba have built a QKD network fairly recently in the last couple of years. Around London, maybe there are some cables carrying some quantum data underneath our feet, right? I mean, so it's around London. China has launched a satellite for secure communication using QKD. So this is quite advanced as opposed to quantum computing, okay? So I'll give you a very quick introduction to quantum computing. Would that be useful? Yes? Okay. So what are quantum bits? So if you're given some basis states like 0 and 1, the state of a quantum system is in general given by a linear combination of the two. And this is called a superposition, okay? So if you have, let's say, 0 and 1, you have a combination, linear combination of the two, and that's written that way, okay? And alpha and beta are complex numbers with alpha squared modulus alpha squared plus beta squared should be equal to 1, okay? And so here is an example. I haven't really used complex numbers, but if you square alpha and then square beta and add up, you get 1, okay? So that's an example of a qubit. Okay, so you have to observe a qubit. So a qubit in a superposition, in general, you don't know the state of the qubit, right? So then you need to make an observation. And when you observe, it collapses to a classical state, 0 with a probability of modulus alpha squared, or the state 1 with a probability beta squared, okay? So for example, if you measure this state, you get 0 with probability 0.3 and 1 with probability 0.7, okay? So that's a quantum state, and then you measure. Okay, so a couple of gates, a few gates. So you can have quantum states and quantum operators, but you can also represent them as circuits with some gates. And this is a Hadamard gate, which acts on one qubit. And this is what creates superposition, okay? So you have, when you apply it to 0, it gives you 1 by square root of 2, 0 plus 1, right? So that's an equal superposition, right? And if you apply it to 1, it gives you 1 by square root of 2, 0 minus 1, okay? So this is a gate that creates superposition. And then there are other gates. These are also single qubit gates. So the first gate is like the NOT gate, but it applies, to the superposition, right? So it flips the 0 to a 1 and a 1 to a 0, okay? And then the second gate shifts the phase, so the plus becomes a minus, and the last one does the phase shift and the bit flip, okay? So the plus goes to minus, and 0 goes to 1, and 1 goes to 0, okay? So these are called poly gates, including the identity gate, which does nothing. And then there are 2 qubit gates, and maybe I'll ask you, what does this do? Any volunteers? So the input 0, 0 stays as 0, 0. So the input to the C0 gate is given on the left side, and the output is on the right. So what does it do? Some students in the audience? Yeah?
If the first bit is qubit is true, then it does not. Otherwise, it does nothing.
Yeah. So that's why it's called a control NOT gate. So thank you. So if the first bit is a 1, then it flips the second bit. Otherwise, it doesn't do anything. Okay. And so it's essentially a quantum version of an XOR gate. Okay. Okay, and unlike classical states, there exist 2 qubit quantum states that cannot be decomposed into a combination of 2 single qubit states. So if you have a state like this, you cannot turn it into a combination of two single qubits, okay? So the point is, if you measure one qubit, let's say the left one, the first one, if you get a 0 there, your second qubit is also fixed, right? Once you measure that, the second qubit will also be 0. But if you get a 1, the second qubit is also going to be 1. Okay, so these are called entangled states. And this happens even if they are quite a bit far apart, right? So maybe they are 100 kilometers apart, but then when you measure one instantaneously, the other is also fixed. So they're called entangled states. Okay, a very simple protocol or an algorithm I'll describe. So it's called quantum teleportation, right? So what you're trying to do is you're sending an unknown quantum state from Alice to Bob, but you don't have a quantum channel. If you had a quantum channel, you could just send it down the quantum channel, but you don't have a quantum channel. So Alice and Bob share some prior entanglement, and they also have a classical channel for communication. And somehow they're able to, using the entanglement and the classical channel, they're able to send a quantum bit from one place to another, okay? And the original qubit is destroyed in this process, okay? So this is a teleportation protocol. So if you look at IBM, for example, you can have this set of gates, the circuit, to execute the teleportation protocol, where H is the Hadamard gate, these pluses are C0 gates, and then that is the measurement, the black dial there is the measurement, and then you've seen X and Z gates as well. So you've seen all these gates. So if you do this circuit and you can run it on IBM quantum computer, and this will teleport one state from Alice to Bob, right? So Alice has the first two channels, and then Bob has the last channel. So whatever you send in the first one comes out on Bob's channel. Okay. Any questions so far? Okay. So you can actually run this, go log into a IBM quantum computer or any other quantum computer. And I did this some time ago. And then the job is successfully run, so you can get an account. And then I get these results. So I sent in 0 plus 1, okay, equal superposition of 0 and 1, and I got these results. This is for 0 and this is for 1. So after measurement, I got either 0 or 1 with this probability. So any idea why the probabilities are different? I sent in an equal superposition, okay, and I should be at the end get 0 or 1 with 50-50 probability. What has happened here? So it's because of the noise in the computer, right? So the free version IBM gives you is quite noisy, doesn't have a lot of qubits, right? And if you pay for the computation time, then you would get better answers, right? So it's quite bad actually. With you get 60% 0 and 40% 1, right? Okay, so this is how it works, and then instead of specifying these kind of circuits, you can also write a program, right? And the IBM uses a Python-like programming language, and you can also write a program to represent the circuit and run it, right? So you can do either. So my claim is that Python is the Fortran of quantum programming, okay? So I think we need special purpose programming languages. So then it enables type checking and reasoning about program correctness. I don't have to sell this to you, right? So we developed this thing called communicating quantum processes. Again, people will recognize the name, right? Why it's called communicating quantum processes. And this is based on the pi calculus, and linear types enforce some quantum principle. In quantum systems, you cannot clone quantum states or qubits. So we use linear types to enforce this. And this was already published in 2005 in POPL and then MSCS journal. There's also been some efforts similar to us. It's called QPL and Kuiper, and Microsoft QSharp is also somewhat along these lines. But ours is sort of based on the pi calculus, and it can be used for distributed computation, okay? Yeah, so the idea is, CQP is the theoretical language, and QtPy is a subsequent implementation. And we developed this especially for quantum computers so that we can take into account quantum effects easily. And we can also run it on distributed systems. And it's also easily scalable, okay? Okay, so here is a quick look at our language. This is an implementation of the CQP language we published in POPL. And this implementation is in OCaml, and you can run this and then you'll get results. So there's a simulator. And this was, by the way, implemented by Richard Bornat, the implementation itself. And people, some of you might know, Andy might know Richard. And I'm one of the few people who can say I've used my PhD supervisor's PhD supervisor as a programmer, right? So he's done a great job. It's programmed in OCaml. And it's also, like, if you're familiar with pi calculus, it's bits of pi calculus with these kind of gates I talked about thrown in, right? And so you can run it and simulate it and get the results. Yeah, so that's the idea. So I won't go through a lot of formal verification stuff, why we need formal verification. These are slides I had for other things, but although I will say something about the CompCert project somebody mentioned earlier. So we have we have techniques like model checking, theorem proving, and equivalence checking and verification. So with QtPy, this was just a modeling language with some type system that you ran you simulated, right? So, but we've also worked on model checking, theorem proving, and equivalence checking in the quantum setting. So I won't give you a lot of details, but I'll give you some idea of that. Again, feel free to ask me some questions, right? And then, yeah. So protocols for quantum key distribution, this is the basis for quantum security, right? Quantum cryptography are ideal targets for verification. Okay, and for example, in the classical case, we've had this Needham-Schroeder protocol, and then Gavin Lowe used model checking to discover flaws in this. So there are, as I said, commercial QKD systems, and we need tools for validating implementations. And some of the networks use quite a lot of classical stuff. So we can also verify classical components and classical protocols within QKD systems, right? But then you have to be mindful of a few things. The state space of a single qubit itself is infinite, right? One qubit, it has complex numbers, so that's infinite. And if you have an n qubit system, it grows exponentially with n. And there are infinitely many possible quantum operators, like I mentioned a few, but any kind of rotation is a quantum operator. So, and quantum measurement is probabilistic. You have to measure something and you get probabilistic results. So it's quite complicated doing any kind of model checking. So we have to make some restrictions on what we can check. So we initially tried to do this with Prism because it's a probabilistic model checker. And we looked at the QKD BB84 QKD protocol. That's the standard protocol for quantum key distribution. And we can do some basic things. We can try and detect, get the probability of detecting an eavesdropper, or the eavesdropper gets a certain number of transmitted bit values, these sorts of things. But then we found that not very adequate. So we developed our own tool called the Quantum Model Checker. And so I'll say a little bit more about that. How much time do I have? 5-10 minutes? Yeah, okay. So yeah, we had a language similar to QtPy, but somewhat different. And then we used a logic called EQPL and QCTL. I'll get to that in a minute. And then we could check in this model checker whether a model satisfies certain properties. Okay, so the logic we use is a quantum extension of CTL, computation tree logic. And so it has some quantum operators in it. And so you can reason about properties of quantum state. For example, we can check whether two states are entangled or not with the logic, right? So that's what we used, and we built this model checker to check quantum protocols. Okay, so this model checking, a lot of this work is with Simon Gay, and the model checking was published as a tool paper in CAV, and there's also a book chapter. And we've also done some work on equivalence checking, to checking whether two quantum programs are equivalent, right? So that was published in TACAS in 2013 and 2014. And also we've done some theorem proving work, and Florian is here now. And we used Cork initially, and then Florian has been using Isabel to formalize some QKD things, and we've also been working on that recently. So we've done quite a range of things in terms of verification. I won't have the time to give you details. And some of this has been funded by VeTSS previously, in the previous edition, when Philippa Gardner was running this. And so some of the QT was published in TACAS 20. And also I've done some work with Mohammed, who's here, on testing in this context, testing of quantum systems. So quite a range of work over a number of years, some of which I'm very grateful to VeTSS for funding that, So, okay, so there are software tools. They are, rather prototypes with PhD students writing some software. So they are available. I'll try and make sure the links work. It's been some time. So if you want to have a look at any of these things. And also one more thing I wanted to mention before I stop. We, as a company, QUÄNTangle, which I formed maybe a year and a half ago, we are part of a Innovate UK project. This is on assurance of QKD, led by British Telecom, with a number of 11 participants, HSBC, Toshiba, and also King's. Mohammed is one of the partners, and Harsh here is helping us. He's working on the project. So the idea is we are trying to use the formal methods, formal techniques we've been developing over the years in the context of assuring quantum key distribution. And like I mentioned, BT has a network, and HSBC, Ernst & Young are using it. And we would like to actually look at some components of that. We haven't got to that at the moment yet. So that's the QAssure project. You can have a look at it as well. So would that be a good time to stop? Yeah, I'll stop. Thank you very much. Thank you. So also, by the way, it's just a minute, Brajesh, in case anybody wants to have a look. So these are quantum chips, right? So these are quantum random number generating chips. So the chips actually work, and you can come and have a look at it. And we've used it, and one of them is in a Samsung phone as well. So this is not, this is all happening now, right? Yeah.
Great, thank you.
Yeah.
It's a brave new world.
Yeah.
So we have time for maybe one question before we break.
Okay.
Dan?
Okay. Okay, so this is probably a little bit of a technical question, so I do apologize to everyone. So I'm not super familiar with what kinds of techniques you can use with these sort of logics for verifying quantum properties, but I know that when you have two entangled qubits, there's this almost causal relationship between them, right? So if you do a C0 to entangle two qubits and then you measure the first one, you can almost reason back in time to say what the behavior of the C0 must have been based on the measurement that you made later. So how well can you reflect that in the formal logic?
Yeah, I mean, you're right. There is, so we don't do that, right? We don't go back and reason. But these are the kind of things, you're right, we could do, right? Potentially. So that's a good question, and it's a good answer, but we can reason about entanglement in general, right? I mean, whether, like I mentioned, whether two things are entangled or not. But you're right. So some kind of causal effect in reverse or something we could potentially try to do. Yeah.
So you think there's an interesting space of research there in terms of formal logic specifically for quantum machines that interacts a little bit more with qubits than what you've got so far?
Yeah.
Okay, cool.
There's a whole field of reversible quantum circuits. There's a whole field of reversible circuit design, and people have looked into some of those. So there is some precursor to it, and there's a conference series called Reversible Computation. So people keep on publishing results about that.
Yeah. Thanks, Mohammed. Yeah.
Okay, I think we'll have to stop there. And there's coffee out in the next room.